the limit, let's say the limit as x goes to infinity, that's a horrible infinity symbol. There's a little better one. Of, okay, 1 plus 1 over x to the x power. What's the form here? What's the indeterminate form? Okay, so inside the parentheses, what happens to the 1 over x as x goes to infinity? What's happening to this term? Goes to 0, right? And what's happening to this term? 0 to infinity then is our, 1, I meant to say 1 to infinity is our indeterminate form. So it's an epic battle, right? Who's going to win? Is this going to be 1? Is it going to be infinity, this limit? Is it going to be something in between? It's an epic battle. By the way, the indeterminate form 1 to the infinity, is that one of the forms that we can use L'Hopital's rule on? No, can't do it. So we need an idea here. What could we maybe do to get that exponent to fall down? Yeah, okay, first let's set it equal. Let's set y equal to that limit. And then the idea is, let's take the natural log of both sides and then take advantage of the power rule for logarithms, right? So if we take the natural log of both sides, we get this. On the left side, natural log of y. On the right side, the natural log of the limit as x goes to infinity of 1 plus 1 over x to the x. So I had a couple people ask me after class, I kind of mentioned quickly why we can actually bring the limit to the outside or ln to the inside, however you think about it. So let me spend a little bit more time on that right now, because since it provided some confusion. Let's put it this way. Let's suppose you have a function f of g of x. It's a composite function, right? And you're taking the limit as x approaches a of f of g of x. Then the question becomes, when can we bring the limit inside? When can we rewrite this as f of the limit as x approaches a of g of x? When is that legal to say that that's true? It's legal to say that that's true when f is continuous. So that's something, and believe it or not, it is something you learn about, or you should learn about in Calculus 1. We're not going to try and prove it here. Now, if g is continuous, all the better, because if g is continuous, then you can use direct substitution and just plug a in for x and evaluate the limit that way. But to move the limit in, we don't require that g be continuous. In fact, it may be an indeterminate form. So is the natural log function continuous on the domain we're interested in? Yeah, it is. So that's what allows us to bring the limit to the outside or the ln to the inside, however you want to think about it. So I'm going to rewrite this then as the natural log of y equals the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. And that's important to be able to bring the ln to the inside, right? Because now we can apply the power rule for logarithms. And what are we going to get if we do that? After the limit symbol, we're going to bring this dude down in front like that. and have x times the natural log of 1 plus 1 over x. But is that the right indeterminate form as written? So after the limit symbol, do we have the right indeterminate form to use L'Hopital's rule? What do we actually have upon substitution? Infinity times, well, okay, guys, if this guy is going, where is this guy going? 0. And then what's the natural log of 1? 0. So this guy, natural log of this 1 plus 1 over x is going to 0. So we're getting the indeterminate form infinity times 0, which is not something that's okay to use L'Hopital's rule on. Is there a way to rewrite this so we have x times natural log of 1 plus 1 over x? Is there a way to rewrite it so that it is okay to use L'Hopital's rule? Well, what do you mean by that? Okay. So you're thinking about the trick from the other day, right? Multiplying by x, or x over 1 if you like, is the same as dividing by 1 over x, isn't it? So let's see if that helps us. Sometimes you just want to try it, see if it's going to work. So if I rewrite it as the natural log of 1 plus 1 over x divided by 1 over x, that's the same thing as multiplying by x over 1. And now is it the right form? What do we still have what? From the natural log of 1 plus 1 over x, the limit of that as x goes to infinity is 0. So we have 0 on top. And what about 1 over x as x goes to infinity? 0 on the bottom. When you're checking for the indeterminate form, that's the only time it's okay to plug in infinity, okay? Otherwise, you're going to write out the limit notation. Because you can't actually plug infinity into any functions, right? It's just a convenience is why we're doing it, to check the form. Okay, so that's the right indeterminate form to use L'Hopital's rule. Okay, so what does L'Hopital's rule say? It says that this limit will be the same as the limit of what? As x goes to infinity. The derivative, respectively, of the numerator and denominator of that fraction we just created. Okay, well, what's the derivative of the numerator? Natural log of 1 plus 1 over x? How about 1 over 1 plus 1 over x times the derivative of what's inside by the chain rule? So okay, this is the inner function. I'm still working on the derivative of the numerator. What's the derivative of 1 plus 1 over x? No, I think you're thinking of an integral. So it's negative 1 over x squared. Is that what you're telling me? Yeah. The derivative of 1 over x, think of it as x to the negative 1 power. You know, use the power rule for derivatives, and you'll get negative 1 over x squared. In fact, I'll put it in parentheses here. So that's by chain rule. So that's the derivative of the numerator. Does everybody agree with that? I'm not going to simplify it yet because I don't need to yet. What's the derivative of the denominator, which is 1 over x? The derivative of 1 over x is? Yeah, negative 1 over x squared. So now you see why I didn't simplify, because this entire negative 1 over x squared will cancel with this one. Everybody see that? Let's clean it up. We get the limit as x goes to infinity of just this guy, 1 over 1 plus 1 over x, which is actually something we can evaluate. By the way, it was L'Hopital. If you want to indicate L'Hopital's rule, it was in this step right here. So put the little h right there. This is something we can just evaluate, right? What happens to 1 over x as x goes to infinity? 0, and then what's left? 1 over 1, or just 1. So, trick question, are we done? It's not really a trick question, it's just an important question. We're not done, right? Because, okay, go back, and what was the left-hand side of the equal sign? ln(y). So, okay, so ln(y) is equal to 1. So how do you get y is the limit we're interested in. How do you get y out of that? Yeah, there's a couple different ways to think about it. You could think of putting both sides as the exponent of e, because if exponents are equal on the same base, it'll still be a true equation. And e and natural log are inverse functions, so the guy that falls down from this guy over here is just y. So a lot of people like to do it that way. So y equals e, that mysterious number 2.718 blah, 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 that turns up in so many different applications in math. Everything from compound interest applications to population growth to AC circuits. E is everywhere in math. Not everywhere, but it's in a lot of places. So that's kind of interesting that we just developed another definition for E. Oh, by the way, it's also the base of the exponential function, right? Which is an interesting function all by itself. Why is that an interesting function in calculus? Well, it's its own derivative, right? So we just came up with another definition for E. It's the limit as x goes to infinity of 1 plus 1 over x to the x power. Okay, so it is finite. So I guess in that epic battle between 1 and infinity, I guess it's not equal to 1, but it's in between 1 and infinity. It's a lot closer to 1. So you're always a lot closer to 1 for any finite number than you are to infinity. So I would say 1 won that epic battle.